Mathematics Level 4, Topic 3, Module 4. Welcome to Topic 3 of the Mathematics Level 4 Support Package, Functions and Algebra. Topic 3, Space, Shape and Measurement. Module 4, Trigonometry. Module 4, Session 1. Session 1 will cover Subject Outcome 3.3, Trigonometry Introduction, Pre-Knowledge and Revision, Trigonometry. We will now watch a video on an introduction to trigonometry.
Hi, I'm Ivan Mapalang. Let me introduce trigonometry.
Subject Outcome 3.3, Trigonometry Introduction. Welcome back. We are now going to work through Subject Outcome 3.3, Trigonometry. This is a difficult area of work for students. It builds on work done at levels 2 and 3, so a lot depends on the students having a good grounding in trigonometry before beginning this section. Trigonometry makes up 25% of Paper 2, which makes it a very significant section of the curriculum. Let's take a closer look at Subject Outcome 3.3 and its learning outcomes on page 10 of your subject guidelines. Subject Outcome 3.3. Solve problems by constructing and interpreting trigonometric models. By the end of the subject outcome, students should be able to use the compound angle identities to derive and apply double angle identities, determine the specific solutions of trigonometric expressions using compound and double angle identities without a calculator, use compound angle identities to simplify trigonometric expressions and to prove trigonometric equations. Determine the specific solutions of trigonometric equations by using knowledge of compound angles and identities. Solve problems from a given diagram in 2 and 3 dimensions by applying the sine and cosine rule. Both compound and double angle identities and all their applications are new in Level 4. Solving problems with the sine and cosine rule in 3 dimensions is also new. Pre-knowledge and revision, trigonometry. Please work in groups to do this activity. Question 1. Discuss and make a list of what students should know and be able to do in trigonometry before they start Level 4 trigonometry. Question 2. Do you find that students are generally well prepared? If not, comment on what the biggest gaps are in their knowledge. Question 3. In your personal experience, what are students' biggest issues with trigonometry? What trigonometry pre-knowledge should students already have by the time they reach Level 4? Let's look at how the trigonometry curriculum builds from one level to the next. First, students must be able to work with trig ratios, expressions, and equations. In Level 2, students are introduced to the 3 basic trig ratios. They calculate ratios in a given quadrant, so they need to understand why a ratio is positive or negative in a particular quadrant. In Level 3, students encounter the special angles of 30 degrees, 45 degrees, and 60 degrees. They learn about the reduction formulae using the cast diagram and cofunctions. Students evaluate expressions in all of the quadrants. They also learn the quotient and the square identities. In Level 4, students combine all prior work and also learn to use compound and double angle identities. Students encounter trigonometric equations and their proofs for the first time in Level 3. They combine all their knowledge to simplify expressions, prove equations, and to solve equations. In Level 4, students also use the compound and double angle identities to simplify expressions, prove equations, and to solve trig equations. And now, solving problems in 2D and 3D. In Level 2, this involves applying trig ratios and the theorem of Pythagoras to find missing information on triangles in 2 dimensions. In Level 3, this is extended to using sine and cosine rules in non-right-angled triangles on 2-dimensional diagrams and the area rule. In Level 4, this is extended further to solving problems in three-dimensional situations. Pre-knowledge is fundamental to success in Level 4. For this reason, we are going to start this trigonometry support module with some revision. Students will need to know the basic trig ratios very well. This is Level 2 work. These ratios are the same for any right-angled triangle. Students need to be able to find the required ratio for theta in triangles in different orientations. Sin theta is the opposite side divided by the hypotenuse. We can remember to use the mnemonic SOH to remember the ratio. Cos theta is equal to the adjacent side divided by the hypotenuse, and we can remember to use the mnemonic CAH to remember the ratio. Tan theta is the opposite side divided by the adjacent. We can remember to use the mnemonic TOA to remember the ratio. We are now going to watch a video on the SO, CAR, TOA tip.
It is advisable and very helpful to design some rhymes that will assist you. For example, we all know the famous for the three basic trigonometric ratios, sine, tan, and cos. You have SO, CAR, TOA, but then you can also use silly old hen, cackle and hackles, till old age, or now, when you do this, the next one you must be very fed up. Oh well, another hour of algebra. But by means of that, you remember that sine is opposite over hypotenuse, cos is adjacent over hypotenuse, and tan is opposite over adjacent.
Students also need to know the trig ratios on the Cartesian plane. Remind students that on the Cartesian plane, we always measure theta from the x-axis in an anti-clockwise direction. Then, the length of the opposite side is y, the length of the adjacent side is x, and the hypotenuse is represented by r. And so the ratios become sine theta equals y divided by r, cos theta is x divided by r, and tan theta is equal to y divided by x. Because we are working in the first quadrant here, the values for x and y are positive, so all our ratios are positive. As we move into the other three quadrants where x and y values are not always positive, the sign of our ratios also changes. We can use a cast diagram to tell us which trig ratios are positive in which quadrants, so that we don't have to work it out manually each time. The mnemonic CAST, cast, should help students to remember these easily. The cast diagram is fundamentally important to Level 4 trigonometry, and students should be able to sketch it quickly to help them with trig problems. Cosine is positive in the fourth quadrant. All the ratios are positive in the first quadrant. Sine is positive in the second quadrant, and tan is positive in the third quadrant. Students need to know the special angles as they will be incorporated into this year's work. They should have learned them in Level 3. It is worth noting that the third triangle would actually look more like a straight line than a triangle, but we have made it look like a triangle for illustration purposes. These are not on the formula sheet, so students need to remember how to make quick sketches of them and fill in all the information. In combination with our trigonometric ratios, these triangles come in handy and should be memorized. They are useful when students need to solve equations or evaluate a function without using a calculator. The question often states to leave the answer in surd form. Students need to be able to find the angle given the ratio and find the ratio given the angle. There are situations where students must simplify expressions using identities such that the whole expression is written in terms of one or more of these special angles. In Level 3, students would have learned that sine and cosine are known as cofunctions. It can be derived from a right-angled triangle that sine theta is equal to the cosine of 90 degrees minus theta, and cos theta equals sine 90 degrees minus theta. Students should know and apply these cofunctions. They are very useful aids in manipulating trig expressions when solving equations or proving identities. In Level 3, Students should also have covered some trigonometric identities. These are also important for level 4. The quotient identity. Tan theta equals sine theta divided by cos theta, and the square identity. Sine squared theta plus cos squared theta equals 1. If you refer to your formula sheets, you will find these two identities are numbers 8 and 9. Now let's listen to a senior lecturer talking about problems faced by students and lecturers in trigonometry.
But now looking at proving of trigonometry, normally the lecturers and the students, I call it tricky trick, because I don't know why trick the people. Because trick is nothing else as the simplification of fractions. Because if you consider your ratios, sine is equal to opposite over a hypotenuse, a fraction. Cos is equal to adjacent over hypotenuse, a fraction. Tan is equal to opposite over adjacent, a fraction. In other words, trigonometry deals with the simplification of fractions. So if you have problems with fractions, obviously you will have problems with trigonometry. If you are strong in fractions, then you will also be strong in trigonometry. And the other tip that I can give you is, each ratio other than sine and cos, remember we have 6 ratios, can be expressed in terms of sine and cos. And that's where your knowledge base comes in, because sine, cos, fine. But now you get something with tan. How will you express tan in terms of sine and cos? Quotient identity of tan, sine over cos. Cotan, how will you express cotan in terms of sine and cos? Cos over sine. Sec, how will you express sec in terms of sine and cos? 1 over cos. Cosec, how will you express cosec in terms of sine and cos? 1 over sine. In other words, whenever you see those other 4, except sine and cos, make it or express it in terms of sine and cos, and then you sit with a basic standard fraction simplification problem. And then with the aid of your fractional laws, you will be able to simplify.
The reduction formulae are also very important to understand from level 3. Reduction formulae allow us to convert trig ratios of angles greater than 90 degrees, that is, obtuse angles, into ratios of acute angles which are much easier to work with. When we determine function values of 180 degrees minus theta, 180 degrees plus theta, 360 degrees minus theta, 360 degrees plus theta, and negative theta, the function does not change. When we determine function values of 90 degrees plus theta, 90 degrees minus theta, theta plus 90, and theta minus 90, the function changes to its cofunction. These reduction formulae are important for simplifying trigonometric expressions. Let's do an activity. Question 1 demonstrates the importance of understanding and using the reduction formulae. In question 2, you need to prove a trig identity. Please work through this activity on your own or in pairs. Let's watch a lecturer working through question 1.
Proof without using a calculator. Sine of 180 degrees plus x times cos of 330 degrees times tan of 150 degrees, tan of 45 degrees, and sine of x. This is once again a proof, but there's certain pre-knowledge, background information that we first need to deal with before we can attempt this question. And the background information here is we need to understand the cast rule. The cast rule. So I will just highlight the following with regards to the cast rule, and then we will understand exactly how I will fit it into that specific problem there. If you look at the CAS rule, it consists of 4 quadrants. You start right here, quadrant 1 goes from 0 degrees to 90 degrees. And in quadrant 1, you will have your special angle. I'm going to use the abbreviation SA. And your special angle refers to angles 0, 30 degrees, 45 degrees, 60 degrees. And all ratios are positive in quadrant number 1. Then you go from quadrant 1 to quadrant 2, which is between 90 and 180 degrees. And the value here will be that 180 degrees minus that special angle. Meaning, 180 minus 30, can you see it will fall in here? 150. 180 minus 60, can you see it will fall in here? 120. 180 minus 45, it will fall in here? 135. Then you go to quadrant number 3, which is between 180 and 270. Please people, this here will be, it's greater than 180, that's why it's 180 plus the special angle. Take note here, no 270s minus, because 270 falls into, and it falls under the Coco rule. In your second quadrant, sine and its reciprocal will be positive. In the third quadrant, tan and its reciprocal will be positive. Then you move from 270 to 360. And that will, once again, not 270 plus, no, 360 degrees minus your special angle, which means 360 minus 30, it's 330. You can already see something there. 360 minus 45, 315. 360 minus 60, it's 300. And obviously here, cos and its reciprocal will be positive there. In other words, an easy way of remembering this ASTC, it's all students, I'm just refreshing, take care. You can see there, all students take care. Right. Now we're going to apply that information inside here. Right. So, as proof, left-hand side. I'm not going to rewrite it, but I'm going to apply it. Sine of 180 plus x, which will be sine of 180 plus an angle. X refers to an angle here, which means that will be in quadrant number 3. And you can all see that tan is positive in quadrant number 3. So that sine of 180 plus x will then become, I like using brackets, minus sine of x. That's the first one. Then cos of 330, obviously it's between 270 and 360. How will you get 330? It's going to be 360 minus, going to become cos of, do all the steps, 360 degrees minus 30. Can you see there? 360 minus our special angle, there is 30. And if you subtract those two, you get 330. Then we come to the next one. Tan of 150, obviously 150 is between 90 and 180. In this instance, it is in the second quadrant. That's why it will now become minus, because in the second quadrant, sine is positive and tan is negative. So you're going to have minus tan of, and in the second quadrant, it will become 180 minus 30. And 180 minus 30 gives you 150. Obviously, sine of tan of 45 remains as is. and obviously sine of x remains as is. I don't think you should have any questions at this stage. Now let us simplify further. This will be equal to, obviously I cannot touch the minus sine of x. This will give me now cos of 30. This will give me now minus tan of 30. Over tan of 45 and sine of x. And now once again you can see we have two different angles here. So we can now just somewhere here in a block sketch our triangles. We need the 30-degree triangle and we need the 45-degree triangle. This is 45, 1, 1, square root 2, and then obviously the 30-degree triangle. That is 30 there, that is 2, this is 1, this is square root 3. And obviously we also need now in this instance so, which stands for sine. You can see we have cos, which means ka, which stands for cos, and toa, which stands for tan. And now we're going to substitute, right? People, I can see that and that will cancel, but I will do that afterwards. So I just keep it at this stage as is. Minus sine of x. And now I come to cos of 30. There's 30 cos is adjacent over hypotenuse, which gives me square root 3 over 2. And then here minus tan of 30, tan toa, opposite over adjacent, which is 1 over the square root of 3. Tan of 45, 45 toa, 1 over 1. And then obviously sine of x. And now I can cancel out what needs to be cancelled out. First thing is work out our signs. A minus and a minus gives me a plus. You all can see that. And then obviously in this instance that will give me, I will have square root 3 over the bottom there 2 square root 3, and I'm getting an answer here of 1 over 2. Therefore, left hand side equals to right hand side.
Now let's work through the solution to question 2. We start off on the left hand side. Left hand side equals cos theta divided by 1 minus sine theta multiplied by sine theta divided by 1 plus sine theta. We multiply our numerators and multiply out our denominators using FOIL. Simplifying, we get cos theta multiplied by sine theta divided by 1 minus sine squared theta. Using our square identity on the bottom line, we get cos theta multiplied by sine theta divided by cos squared theta. Dividing the top and bottom by cos theta, we get sine theta divided by cos theta, which we can simplify to tan theta using the quotient identity. Tan theta is equal to our right-hand side, so we can conclude that left-hand side equals right-hand side. We have successfully proven our equation to be true. Now here's a lecturer with some teaching tips on proving trig identities.
Let's start with a proof. We need to prove a left-hand side equals to a right-hand side. There's 3 ways in how we can attempt this type of question. The first one is you can look at the left-hand side and you can prove it exactly equal to the right-hand side as it is given. The second one is you can even start at the right-hand side and then you need to prove it equal to the left-hand side. And the third kind of approach is you can simplify the left-hand side up to a certain point, and then simplify the right-hand side to that same point so that it's exactly equal. And also one thing to take note of, when you need to do a proof, your starting point always be look at your right-hand side. And as you move along simplifying that proof, always consider the right-hand side to make sure that you remain on track. And if you apply the laws correctly, you will automatically end up getting the right-hand side. And that's, in a nutshell, simplification of trig identities.
Here are a few more tips and a general approach for proving identities. Start with the more complex side of the equation and simplify it to look like the other side. If both sides are equally complex, try to simplify both sides. It often helps to write tan theta as the quotient of sine and cos. If you spot that there is a tan on the other side of the equation, then you may need to do the reverse. If there is a sine or cos squared with plus or minus 1, then try applying the square identity to simplify. If you need to add or subtract fractions, find a common denominator. Factorize if necessary. Working neatly and systematically is the key to finding a proof that works.